Thanks, Professor Law, Professor Zhang, and others for giving me this opportunity to share my research with you. And I also I stay here for a whole week. So far, I enjoyed this so much. The host is Professor Law. So on the screen, you say this is a new watershed diagram published by USGS a few years, maybe just 1 year ago. And different from other watershed reviews, you can say some human activities, such as reservoirs, and you say reservoirs, groundwater recharge, hopefully artificial recharge, and water uses. And an interesting thing here is that Streamflow through closed basins. So this is the kind of interbasin water transfers from one basin to another basin. So anyway, so this shows the review of USGS on watershed as a coupled nature healing systems. And it also highlights the research on how could we factor human interventions in hydrological systems. So we have various different healing interventions, and traditionally hydrologists consider land use change, agricultural runoff. We call those interventions, they have indirect use of water on stream flow. But there are many other forms of interventions. They directly affect the stream flow, such as dams, hydraulic barriers. Hydraulic barriers, they build, recently in China, they are building a barrel, a dike between one of the largest lakes in China, downstream of Yangtze River. Because the lake and the river, they are naturally collected. Now they are building a barrel over there. So then they could control the flow in the lake. Water withdrawal, of course, irrigation, right? And also return flow from industry or from irrigation, groundwater pumping, drainage practice, especially in the West, in central, Middle West, they have a lot of tile drainage systems. And one more is the interbasin water transfers. That's also highlighted at the USGS platform. So then we have many observed hydrological changes due to different types of irrigation. And those are probably at the scale of stream, maybe local or at stream level, at stream flow, sediment dynamic change, and the temperature and the water quality change. Many cases are due to, and also the evaporation pattern change. And the last one was the topic of regions species. Basically, he works on how human activities affects the intra-year and the inter-year ET variation. Then at the basin scale, we say there's some storage and cycle variation. And we also say hydrological activity changes, alteration of evaporation around the tissue at the basin scale. So that's basically this relates to the particle curve, specifies the relation between evaporation and runoff. But recently we found that relationship has been altered in some basins. Then, of course, groundwater, the shift of groundwater dynamics and water balance change of crossing basins due to interbasin water transfers. So this is like an overview of there could be more, right? You could identify more. So I just recently, I heard a presentation that said how the reservoir operation in upstream reservoir operation changed the groundwater and surface water interaction downstream, and then changed the contaminants in the groundwater. Something interesting. So basically, hydrological systems we define them as a coupled nature human systems. The interactions of these two components, two systems, end with the so-called self-organizations, adaptations, especially on the human side, and also the emergence of some new patterns. And both systems share some cause the loss dependencies. So there are some challenges. Although we know is we should quantify rapid and reasonable human interventions in hydrological processes, hydrological models, but there are some challenges. So one is the data deficit. We have incomplete or no records on some human interference. For example, for reservoir, that's my current major work. So we try to assess the data availability for reservoir operations, then we could records and reservoir models. So I'm going to talk about that later on. The second issue is the so-called oversimplified or too complex modern representations. So that's actually related to the third point, the mismatch between hydrological and water management modern communities. I'm not sure if you agree with my statements here. The hydrological models adopt oversimplified human representations. Do you agree with that? So maybe you're doing better, right? But I'm working with a group of national water model, right? National water, even for reservoirs, they are still using it's called poor level model, right? This is basically the simplest, probably oversimplified form of reservoirs. The other way is the decision support systems on the water system side. Those DSS, they are often based on simplified hydroclimatic processes. Do you agree with that? I kind of agree with that because my major work is more system side. They often, so I just remember many years ago, I worked out my first, my kind of global food and water model. And we used the first global model, which is called water gap, right? Created by Ecuador. Then I met some hydrologists. They said, "What? This is just the first model." So I don't believe that. There's no data. They say, "All right, so your food water model depends on that. Will also make not much sense." So if you review the DSS by federal agencies, Federal Bureau of Operation, Army Corps of Engineers, many others, this is still an issue based on my observation. All right. So okay. So that's I summarize like this. Both water resources modeling and management practices, they highlight the need to incorporate realistic representation of both human and natural components. But there was some recently there was some progress. I like to share with you my observations. First, of course, is the growing data on water management activities. So we often say we need to know the behavior data of water managers. How could we know that? Social media. You may not believe that, right? Social media might provide us some reliable data. So one of my colleagues, he's a computer scientist. He's a pioneer in the social sensing, and he said the purpose of social sensing is to obtain reliable data from unreliable sources, technology, right? And also remote sensing, right? It has played a central role in providing many consistent global data sets like reservoir, right? We have many global data sets for reservoir surface, reservoir storage, and also other things, right? It helps a lot on agricultural water use and on water quality too. And then machine learning, AI and machine learning, they have made it possible to leverage improved data availability to develop more realistic representation of human activity. I have some examples for that. All right, so based on what we have, so one of my PhD students, he developed, it's called data inventory. He called that as data IH2. So the idea is we got what we have. We try to get the best, which is in the literature, on different things. dams, agriculture, urban use, and other things. But we make it open. We hope this could be a community resource, and other people could add to that. So that's why we call that as open, kind of open community resource. And actually, recently we published a paper in WRR. The data we have recreated, we have generated is already available. So this paper just lists all kinds of human intervention data we could find from the open data sources, and of course also from our own work, especially on the reservoir side. So for example, for reservoir, you can download the inflow, daily inflow and outflow for more than 15 years for 450 reservoirs in the United States. If you want to study reservoir, you can download that from HydroShare. Okay. And many of these data sets, they are based on remote sensing or based on some local records. And so you might want to, if you are interested in water uses, so I believe you might remember the USGS data, water use data, right? So just a few years ago, what you could get is the data updated every 5 years. And the quality is not reliable either. Just recently, they published much better data. I mean, as they claim, okay, is basically, is first of all, the old data set was for county level, but now it's a half file, it's smaller, it's sub-county level. And also they have monthly data. So that, anyway, there are many progress. Now we have journals, right? We have data, scientific data. We have many other data-oriented journals. So these journals are published some data sets which could be shared with the public. Okay, so now next, I'm going to talk a little more about how we incorporate human interventions into hydrological models. So that involves several steps, several issues. Okay, first of all, how could we represent, or in a better language, how could we quantify different type of human interventions? The second is that, so many of our colleagues, hydrologists, we work on model calibration, hydrological model calibration. But when we add human components, is this just like a business of usual issue? We use the same approach as we used before to calibrate our new model, or we might have some new issues. It's a question. Okay. How can we test that? Right? How can we test the reliability of the model? So let me start with the representation. I use reservoir. So first of all, let me talk about the criteria to represent human interventions in hydrological model. So first of all, because normally in our hydrological model, physically based hydrological model, everything is apparent, right? Everything is apparent. It could be it could be explained. So if we should not add a black box, right? Black box on human part. That may not be consistent with hydrological models. So anyway, it should be we call this as the interpretability. Second one is some people said, oh, anyway, I have already done all you said, because in my basin, I incorporated a very good, very advanced reservoir operation model to a SWOT model or to wake model, to a hydrological model. That's fine. That's fine for your watershed. But we are targeting a region, national model or even a global model. Right? We want something general. So that's what we talk about generality and the compatibility. I still use the example of reservoir and the hydrological model. If your reservoir model is a multi-objective optimization model, to run that model might need half an hour. Then I mean, you can do that with your individual watershed, but it's not, you cannot expand that, right? Expand that to other regions because it's not compatible in terms of the computation time. And of course, it should be reliable. Let me use a reservoir as an example. So in the past several years, so my group, we spent some time on developing the so-called generic data-driven reservoir operation models. It's called GDROM. And so we only use 4 inputs: storage, inflow, PDSI, that's a drought indicator, and the day of the year to represent seasonality, right? So using those 4 inputs, we try to determine the daily reservoir release. So you can say none of these inputs is reservoir related. In other words, we don't ask for reservoir size. We don't ask for the function of the reservoir. So that reflects kind of generating, right? And then we also use our parent structure of modules under transition conditions. So I will not talk about the techniques because it's already published for a couple of years. But I just want to say, so based on long-term data, so we could derive an apparent structure of reservoir operation. So in simply speaking, we can write text file. Okay? We can simply write an if-then rows, a text file, and then we could incorporate the text file to other routines. So this is as I mentioned, we collected over 15 years daily data for 450 reservoirs, and this is a map of the reservoir. They include different reservoirs with different primary functions, flooding control, irrigation, and so on. But what we found, is that we try to develop some basic modules for reservoir operation. So what we found is that, so for many of this reservoir, there is actually one module. So that means maybe the flow is constant. For recreation purpose or for irrigation purpose, the release is constant, simple one. And some of the reservoirs, they have 2. Some reservoirs, they have maybe 4 or 5 basic modules, because those reservoirs, they might have multiple functions: hydropower, irrigation, or flooding control, irrigation, right? And then they need different modules for different time period. Very rarely, only few reservoirs, they have like more than 6 modules. So we got excited for this because we found out for reservoir operation modeling, actually, we just need to know the basic modules, right? The several basic modules. It's not like we have to consider about 10 modules, something like that. So in that case, the model might be more complex. So actually, the reliability is quite good. So basically, we as shown from this figure, we show basically the NSE and the BIOS, right? NSE and the BIOS for those 450 reservoirs. And more interestingly, the GDROM could catch operational dynamics. So over here, for this particular reservoir, Bighorn Lake, we identified 5 modules. Okay, 5 modules. So from this is a storage timeline, a time series. This is a release, right? And now we can say the different colors represents the use of different modules. Okay. So for example, for the storage, and by these different colors, we know which module was used to determine the storage and the release. And so you can see that around this time period, maybe starting from 2000 and ended about 2008, you can see this this module 2 is in red. It's more often used. This is because this is mainly because it's a dry period. Right? It's a dry period. So that basically shows the data-driven module could catch the impact of hydrologic variability. And then we also, real quick. And we also found out the model could catch the long-term, long-stationary changes, the pattern change, operation pattern change over years. So this also shows the Taylor Park Reservoir in Upper Colorado. And for this reservoir, we identified 4 modules by different colors. And here we show the days of a year. We have 365 days. And on this side, we show years, right? We show the years. You can say in this part from 1990 to 2000, this yellow one, basically module 0, is used a lot. And then because of the drought, impact of drought, there were several years drought events, starting from 2002 and ended with about 2008. In this time, you can see that the module is shifted from module 0 more to module 3. And by the way, these 2 modules, they are simple ones. They just represent the constant flow. So in this dry years, the module is shifted to a constant module with lower value, okay, with lower release value. So basically, this diagram just shows over years, how reservoir operation has been shifted over years. And we could use 4 modules to represent them. Okay, just like a summary, how could the GDRAMs, why we try to promote the GDRAMs as a general representation of reservoir in hydrological models? For the interpretability, first of all, we say it has a parent structure with only 1 to 8 basic modules, and it revealing the operation dynamics and the operational behaviors, especially in the dry period. So in terms of the generalizability, we only need 4 common inputs, and they are independent with reservoir characteristics. And the other thing, we have 5 typical types of modules. I did not mention details about that. So the reservoir the 5 basic modules, they are basically, some reservoirs, their operation is very simple, it's constant. The release is just constant over years, over days. There are another one is constant, is piecewise constant. At a different flow level, they have a different constant levels. But some reservoirs, they are constant by different storage. So at a different storage, they have a different constant level. And in some cases, that's usually what we think, right? So it changes with a linear relationship between inflow. Okay, so we have higher inflow, they will have higher release. Right? This is what we usually think. And there are more complex cases, it's a nonlinear relationship. Right? It might change it's a nonlinear relationship with storage or with inflow, basically with water availability. So those are the 5 basic components. So sometimes I talk to my students, I say, think about how can we build a reservoir optimization models. It looks like you only need, you are given 5 Lego pieces, right? And you try to put them together. You try to put this 5 Lego pieces at a different time point. That's your model. And now the student is working on his PhD thesis. So hopefully he could end with a kind of new model. So that's also, I mean, generally they say, if we learn something from data, and then we bring it back to our traditional modeling, like optimization, that could probably help us a lot. So compatibility, that's it. So basically we have, GDRAM has a simple structure. It has explicit input-outflow relationship with rainfall runoff processing. And it also tested and ready to use for any watersheds watershed rainfall runoff modules. Actually, we are working with LOA Climate Research Center and other agencies with LOA to add this reservoir representation into national water models. So we tested the reliability even for basins for some reservoirs with limited data, and we did some transfer learning and used some patterns we obtained from data-rich reservoirs, right, to build models for data-limited reservoirs. That's basically the advantage of machine learning techniques. Okay. So here I just have one slide to show our testing with national water model, testing of the. So it's a little complex here. Let me put. So we have red color and the green color. Okay. Red color means that we found out national water model. They are not perfect, certainly. So many of their inflow forecast has negative NSE, basically has negative matrix NSE. So we separate them. Because thinking in this way, if inflow is not reliable, it's wrong, then how could you expect the outflow is right? Right? So that's why we separate them by different colors. And then we compare these two. We compare KGE, NSE, and RMSE, different metrics. And we compare the original national water model and the national water model plus GDRAM. Basically, we replace the simple reservoir representation in national water model by GDRAM. And you can see that especially for more reliable inflow forecast, the below part, so we have significant increase of KGE and NSE and the reduction of RMSE with GDRAM, right? And I also we say they reduce the range. That's also important, right? Not only the mean, we say they reduce the range for the cases with GDRAM. So we also did this for some watershed models, which is also published in recent years. All right, now I just talked about the representation, and let me move to say a little bit about the calibration. So I mean, we know we have not done a good job in representing human interference, human interventions, but we still calibrate our model to high NSE, right? Almost to like say, oh, my model is perfect because my simulation fits the observation totally. Why? How? So the reason is that you transfer the error, right? You transfer the error to your parameters. So one of my early PhD students, actually, he checked. So if a reservoir is not represented well over there, then they just found the calibrated parameters like this soil parameters, land use parameter, they are out of range. They don't make any sense, right? So when you calibrate your model, not only you focus on this NSE and other metrics, you also need to look at the distribution of your parameters. Do they fit into the reasonable range, right? So now I give you an example. This is with a watershed model. And so here we try to compare our GDRAM model with other popular reservoir representations used in global hydrological models and also national models. And we compare three parameters. We compare the different models with observed, right? For depth of soil storage. This is one of the parameters used in the watershed model. So we found out with GDRAM, we could basically catch the pattern, right, as observed. And other models, they ended with a kind of shift, kind of right? Kind of value shift of the observation. But some parameters, probably they are not really affected by the reservoir operation, then we don't find much difference. For groundwater recession coefficient, actually this one, we also found out with GRAM, the calibrated parameters is more reasonable compared to others. Right? Like if we look at this one, this is a ISTARF, right? ISTARF. This also is widely used reservoir module today. So you can see that their model end with a shift, right? Into the quite big shift compared to the observation. So that basically says if we have better more realistic representations of a Ximing intervention, one of the benefits is that we end with more reasonable parameters. That's not only the mean, we should also check the distribution. All right, so now the next thing is about the testing, right? How can we test the performance of a model after we add some human representations? So this is the early work. This is my early work. So here I just want to say many human interventions like reservoirs or water withdrawal or pumping, and those things, they affect low flow more often, more frequently than high flow. Of course, reservoir also affects high flow by flooding control, right? But if we look at in general, we found many human activities that affect low flow. So this is a work from probably one of my early PhD students. He basically showed this. This is a famous log linear relationship used in flow recession. But we found out because of the water withdrawal, in recent years, the relationship, the log linear relationship developed by Professor Brozaha is a canal professor, right? So he published a paper. He showed that for flow recession, we should have this log linear relationship. But he only tested his results with the so-called natural basins, natural watersheds. So after we considered the human interference, the log linear relationship may not exist. So this says should we, when we add human interventions, should we put more attention on the low flow change? But meanwhile, we know many of our, like NACE, right? Many of our goodness of fitness, they probably have a better priority, higher priority on high flow or kind of regular flow. And they probably don't put much attention on the low flow. So this could be one issue, right? The other issue is that the same here, yeah. So like the indicators of go back. The indicators such as NSE, they also have some variation of crossing samples. Variation crossing different samples. So actually, this is not our work. This is also a recent water resources WRR paper from Professor Richard Vogel's group. And basically, they showed if we move to log NSE, which has a higher priority on low flow, then the issues could be improved a little more. All right. So now based on this, the representation, calibration, and testing, and so we try to do anyway. We ask ourselves some crucial, important research questions. The first is when, where, which, and how do human activities impact natural hydrological processes? So our current work has addressed some aspects of this, but there are also left issues. Right? And the second one is where and what do we need to improve in terms of data and modeling capabilities. So that's the second question. And the third one is how do impacts of the human activities scale from local to basin scales. Right? So the scaling issue is a fundamental thing in hydrological modeling, right? But if we add human activities in, so what is like additional perspective, additional dimension for us to address the issue? Now, to answer these questions, we developed this basically the title of my presentation. We call this as diagnostic framework and data inventory to analyze human impacts on Streamflow. Okay, I need to check my time. Sorry, I probably talked too much. 40 minutes. All right. Let me try to finish this within 20 minutes if I can. All right. So basically, we used anyway. It's hard for me to explain, but on the hydrological process side, we try to use a calibration frame model. It's based on the body control. The reason is that we want to assess the impact of different human components. Right? We don't want that to get mixed with the traditional hydrologic processes issues. So that's why and then we consider about a series of human interference. So we use the Mississippi River Basin as an example. So actually this basin covers different climate zones. And also it has quite heavy irrigation waterways role, right? Especially on the western part. And huge number of reservoirs for different purposes, right? Like flooding control, irrigation, and other things. So now, so this is a kind of general figure to show how with our own reservoir component, how the model performance is improved. So basically, this is the KGE without reservoir representation, and this is the KGE with reservoir representation. So we basically say, especially when the KGE is low, right? When the KGE is low, and we have quite significant improvement of the KGE values. When the KGE is already high, we don't say much. That's probably we don't need. Right? We don't need to account the reservoir operations in some places. And also, let's say the hydrological model captures the different seasonal influence of various reservoirs. So so the red color here shows the decreased flow. The blue one shows the increased flow. And here we say the flow change, right? It either increase or decrease the flow in different months. Yeah, and in some months we especially on the main stem, we say the blue color. That basically says in this low flow time, the reservoirs basically increase the low flow, right? In the high flow periods, especially in May and June, and the flow is relatively high, and the reservoir there reduces. And this is basically just reflects what our observation. Sorry, this one is probably the most difficult figure I want to explain to you. All right, so let me explain. First of all, we use KGE, different components of a KGE in terms of the variability, bias, the timing, and also the total. And we look at 3 sub-basins in Mississippi River Basin, Missouri, Arkansas, White and Red River, and Lower Mississippi. And so here we try to show the improvement, different level of improvements from green to blue, and then basically different levels of improvement. And also the size of the circles represents the percentage of gauges. What is the percentage of the gauges being affected? All right, and then we have 4 modeling designs, right? So the first one is just the natural system plus reservoir. And then step by step, we generate a sequential interventions. So for example, for scenario 2, we use module 1 plus interbasin transfer. And for module 3, we add irrigation and so on. The last, we add water supply, right? So what we expect is because we got from 1 to 4, we have more human we have more representations of human interventions. So we expect the results could be better, right? So now let's look at the Missouri, right? So we find this blue color that basically shows a relatively high, right? It's not the highest, but it's relatively high improvement in terms of variability, KG variability, and the BELS. But if we add irrigation, then the improvement will be the largest. Level. That basically shows in many places the reservoirs are used for irrigation. If we put a reservoir there, but we don't put irrigation, then we don't expect good improvement. Then in terms of, we have the similar observations with in terms of the total kg, right? Okay, so that's another difficult figure, right? Basically the same definitions, but here we want to show the impact of the modeling results on different levels of flow. So this P10 and P90, they are long exceedance probability. So P10 represents the floods, high flow, and P90 represents low flow. Okay, so now we still use the Missouri as an example, right? So now if we say we add reservoirs and then we add interbasin transfer, not much. We have improvement with high flow. We have improvement with high flow. But for low flow, if we just add reservoirs, the results are even worse. Right? The results for low flow, the results are even worse. And even after we add the interbasin transfer, doesn't change much. Only after we add irrigation, then the deterioration, then the results becomes much better. Then we can say some green circles on this side. Right. So that basically shows it's a simple, it's kind of intuitive results, but it's nice to say to some more detailed numbers, right? So if we really need to put reasonable reservoir and the irrigation together for some sub-watersheds in Mississippi River Basin. Right? If we miss one of them, then the results could even be worse, especially for low flow. Okay, and then we also, this is the impacts of human interventions. They differ in directions, magnitude, and scale. So here I just have a summary. Irrigation tends to reduce flows, right, as we show from this figure. And artificial drainage, especially in Middle West, in Middle West, artificial drainage increases the inflows. And then what about the urban? So actually we don't find, so we might think about we have so many urbanized areas in this country, right? So they might affect the hydrology stream flow a lot. But based on our current results, we really don't find out very significant impact. right? Especially at the annual scale. So if we look at monthly scale, so this is the impact of irrigation. So we could say some different patterns in different months. And this is drainage. And for urban, especially for urban stormwater management, so in some months, right? In some months, we could say a little some better changes. So we currently, to be very honest, we don't have a way to, especially the hydrological model does not really have a reasonable representation of surface groundwater interactions, right? But we are lucky. For some reason, we found out the results are not very disappointing. So like this one basically shows the non-renewable groundwater pumping. You can see in this region, in this part, we have looks like we have large values, right? Unfortunately, there's some way consistent with the USGS measurement. But there are also some very disappointing results. So this one basically shows the flow in this relatively small river, Platte and also the Arkansas. So here in this red color or pink color, we shows the model results, and the the black numbers shows the observed based on USGS stations. So you can see that they are not consistent. Especially, in this part, but based on our model, right? It says the flow will increase. In downstream, we got more inflow, right? We got more lateral flow, should increase. But the observed flow is reduced a lot. So simply, this is a reason because there is a canal which diverts water from this point to another region, but our data did not. Our data does not don't catch that. The same thing for Arkansas. So you can say from this point to this point, the observed stream flow almost decreases to dry. Almost nothing, right? From 7.3 reduced to 0.1, right? Our model results, we still show the continuous increase. The reason is that in this part, there are basically two reasons. One is that there is a lot of groundwater pumping, very active surface and groundwater interactions. The groundwater pumping depletes the river flow. That's our explanation. That also shows the issues. Where we have to either correct the model structure or we get more data on the human parts. So let me be a little quick. Sorry for I usually I cannot control my time well. So basically we just created this. First of all, I want to highlight the national inventory of human data sets. And so we hope more people in the community can add to that. Once you generate new data, you can add to that. And also our results basically shows the joint impact of multiple human interventions. And we need to consider about the joint impact of different human activities like reservoirs and irrigation. So the third one is that we don't say we generate a good model for people to use, but we want to highlight this is a diagnostic framework for people to find out what is the improvement, why, and what do we still need to work on in terms of data and model structure. So I already regarding the facial research questions, I already mentioned some of those in my early slides, but let me just skip this one, and I hope I could spend a little time on. But more importantly, we hope we could keep updating this data inventory, and then this could be shared with any modeling groups. So yeah, let me spend a little time on regarding the discussion. The first, I mean, everybody wants to talk about the role of AI or machine learning. So for we also think about this issue is like we cannot expect the same water availability from different regions. So in some regions we have relatively good data availability. In other regions, maybe not that good. So how could AI, like transfer learning, could help us, right, to get some insights about data patterns, and then we could still do something for data limited areas. Right? That's the issue. And the other one is that basically we focus on the interacting human interventions across the scales. So as I already showed in like the kind of the joint impact of reservoirs and the irrigation, and this impact may not be linear, right? May not be linear. So and here we only look at the impact on Streamflow. There might be different patterns, different impact patterns on other hydrological processes. So using the data set, we might be able to explore more. So today we already expanded the boundary of water resource systems to the so-called food, energy, water nexus, right? So we already have some models on that. So that basically, for me, I think anyway, on the management side, that makes the infrastructure and the institution more complex. There's couplings of infrastructures and institutions from different sectors. So that makes the representation of human components even more complex. Right? So that could be left for our next generation to address. So the last one I want to comment a little bit is about the integration of social and hydrological science. So I want to say we are not on the same line of social hydrology, but we are on the line of how could we quantify human interference in hydrologic systems. Only one way. But my understanding of social hydrology is that we also want to address the other way, right? We want to also address how the hydrologic alterations affects the human side. I mean, in a relatively long-term framework. I have to say that's this two-way. This two-way dynamics have not been addressed in my own work. Right? But I really hope anyway. So we could work with more social scientists and get their data, and then we could probably someday we could implement this two-way dynamics. So kind of take-home message is that first of all, we want to promote a holistic systems approach to simulate complicated multiple human interference and their joint impacts on interconnected hydrological processes. And also, I hope we could expand this diagnostic framework and data inventories and make them a community tool which could be shared with people. And then we could work together to address human interference on different hydrological processes. Thank you very much.